Hi guys, so today we're going to do the editorial for this problem tokens on a tree that is from the May Lunchtime 2021 division. I think it was in all divisions. I think I have currently opened the division 1 version, but I think it was in division 2 and division 3 as well. So yeah, so let's talk about this problem tokens on a tree with the problem code TR tokens. Okay, so in this problem, what's happening is that we are given a rooted tree with n nodes and one is the root of the tree and some of the nodes have a token in them. So in one move, what you can do is you can choose a non-root node and take that token. But if its parent doesn't have a token, then what you can do is in one move, you can move the token from this node to its parent. So what is the maximum number of moves you can make? So something like, wait a second, what is it? Hmm. Yeah, so when it becomes empty, the other can move there. Okay, right. So it is something like, let's say if we have a tree. So we can have a tree like this, an arbitrary tree, and a few of these vertices on the tree have some tokens on them, something like this. So what we can do is we can choose a token, like we can choose a vertex which has a token like this, or this. And then once we choose it, what we can do is if its parent does not, like this is the root, so obviously everything has a defined parent. And if its parent does not have any token, like for example here, this has a token, but its parent does not have a token. So what we can do is we can move it upwards like this, something like this. So yeah, so that's what we can do here. And these type of operations we have to do as many as possible. So what's happening is that, for example, if there was a token here, then this operation wouldn't have been possible because there's a token here already. So in one vertex, there cannot be more than one token, and we have to do as many moves as possible. So how would the tree look like in the end? So let me try to make the tokens with yellow in the end. So this is the final configuration. So this would look something like this, more or less. I'm not making the exact configuration for this result, but it would look something like this. What would be the characteristic? The characteristic would be like root would have a token unless there are no tokens at all. Root would have a token. That is one thing. And the other thing is that all tokens will be connected. Will be connected. So why they must be connected? Because if they are not connected, that means we can do at least one more move. So something like if root has a token and then a few others have a token and then some part is disconnected. So if there's a gap in between, what can happen is we can do more moves. So obviously everything has to be connected and root has to have a token. And there are other constraints as well, like from one subtree only that many number of tokens can come, that many, like the amount of tokens that are already there, something like that. So yeah, so that is also a rule and we have to take care of all those things. So let's try to do it greedily. So how will we do it? So first of all, let's try to break the problem into subparts. So something like, yeah. So let's say this is the root. To solve for this, what we will try to do is first we will solve the answer for this subtree, then this subtree, and then using these two answers, we will try to find this answer. So that is like a very common thing. Uh, Solving problems using DFS or DP1 trees. Um, this is like a common thing. So what we will try to do is, let's say if we have a token here and a token here and a token here. So what we will do is when we solve for this subtree, obviously we will move this upwards and that's the best answer. So we make it with yellow. So this is the best answer for this subtree. And for this subtree, any one of these we can move upwards. So the best answer will be something like this. Let's say we have a yellow here. And if this one moved upwards, then this also is a yellow. Let me make it half red, half yellow. Like this. Right. So now when we know the answers, know the configurations for this and this, what can we do for this one? So we know that we can either move this upwards or this upwards or this upwards. So when we move, like obviously we cannot move this upwards, but what we can do is we can move this and then this. So automatically that will be the same thing. So my question is, should we move this one or this one? Because moving this one step upwards and this one step upwards is the same as moving this directly two step upwards. So which one should I do? Should I move this one or this one? So obviously it makes more sense to move this one upwards because this will give us more moves. So obviously this gives us only one move, but this gives us two moves. So obviously, this gives us one move and this gives us two moves. So obviously this one is correct, and that will give us the final configuration. Let me make it with blue. So here we will have the final this thing, and here we will have a final, and here we will have a final. So yeah, something like this will happen. So the key idea of this problem is that to solve for any root, what we will do is consider all the subtrees of that. So these are not just nodes, these are subtrees. Consider all the subtrees. Then if this has a token, then obviously we cannot do anything. Just store the answer as it is. But if it does not have any token, then what we will do is we will take the deepest path or the longest path of connected tokens, and then take the last one from there and take it out from there and put it here. So, yeah, so that's what we want to do. For example, if we had something like, let's say, if we had a tree like this, yeah, something like this. Okay, right. And if the tokens were like this, 1, 2, 3, 4. Yeah, let's say if the tokens were like this at any arbitrary step, and let's say using all this, I have to find the answer for this one. Then what I will do is I will see among all these, and this also, let's say here also we had a token. Then we will try to see the depth of everything. So this has the depth only 1. Here I have depth 1, 2, 3, and here I have depth 2. So finally what I will do is I will choose this 3, remove it from here and put it here instead. So yeah, so this is what we have to do. And now the question is, how can we do it? So we want to find the answer for a certain subtree, and then we want to store all the different depths at that subtree, right? So that's what we want to do. So again, let's say if we had a tree and multiple subtrees like this. So what's happening is that, especially like in this case, let me just undo a little. I cannot do that. Okay. Yeah. Anyway, so when we had the red tokens here, then the depths were like 1, 1, 2, 2, 3. So it doesn't matter which 3 is connected to which 2, because after we remove the 3, all the 2s will be the same. So, and we are always taking the biggest element. So we can represent this entire thing as just a 1, and this entire thing as just a 1, 2, 2, 3. So yeah, so that's something that we could do. So yeah, so that's what we will do. And for that, what we can do is on each of these vertices, on each of these subtrees, we can store a multiset. Multiset of depths. So we can store a multiset of depths, and then when we want to get the multiset for this element using all these multisets, what we can do is we can merge all the multisets. So we can just merge everything. Then remove the biggest element. If this is empty, then remove the biggest element, otherwise insert a 0 as well. And then after that, one thing that we have to do is add 1 to everything, because when we move upwards in the tree, obviously the depths will increase by 1. So this solution, I think, will be n square log n, something like n square log n, because it takes log n time to insert or erase any element, and then we will merge all the sets and everything. So each time it can take n log n, and there are n vertices. So n square log n total time it will take, n square log n. Yeah, so this much time it will take. I hope this is visible. Let me write it here. N square log n time it will take to do all of these steps that I told. And let's see how many subtasks we can pass with that. I think this one should pass, but these two will fail. Okay, so you can get 31 points. Yeah, so you can get 31 points using this. Now to actually improve it and get a AC solution, what you can notice is that there's a technique that is called SAC, or sometimes it is called DSU on tree, or it is just small to large merging. So this is like an interesting concept. I'm not going to go in much detail about that. But what's happening is that normally, in any problem, let's say if we have some sets or multi-sets and we have to merge everything, and if we just ensure one thing, that we always merge the smaller set into the bigger set, smaller set into bigger. So if we always make sure that that we merge the smaller set into the bigger set, uh, then what will happen is any element that is in the smaller set, when it leaves the smaller set and goes to the bigger set, what happens is that the size of the set in which that element was present gets at least doubled. So if it is getting at least doubled, how many times at max we can do this step? Obviously, we cannot do it more than log n times, because after log n times, the size of the set will be n, which is the size of the entire thing. I mean, the it is the size of the total number of nodes that are there. That is n. Obviously, it will be 10 to power 6. So obviously you cannot have more than log 10 to power 6 times when an element from the smaller set moves to a bigger set. So the total time complexity of such a method becomes n log n. N log n times you will put an element from one set to another, multiplied by the time complexity of the set, whatever set you have, the time complexity of that. So usually when we use a multi-set or any type of set, it is O of log n. So this thing becomes O of log square n. So yeah. So this is a solution that we can use. If we actually use SAC, then we can do it in O of n square log n. But let's see another improvement that we can do here. Maybe this might TLE. But yeah, this will give you the correct answer on this subtask. So you'll have most of the points. But here it might TLE, because the reason it will TLE is that multi-sets are really slow. Multi-sets are really slow. So I'm not saying you will definitely get a TLE. You might get AC as well. But yeah, so there's a good chance that you might get TLE. So yeah, multi-sets are really slow. So what we can do here is, instead of using a multi-set, we can use a priority queue instead. So we can use a priority queue instead, and long story short, it is actually much faster, right? So the reason is that multi-sets are based on arbitraries, and priority queue is based on heaps. I think it is Fibonacci heap. I'm not very sure, but it is some type of heap. So yeah, so this is based on arbitraries and this is based on heaps, and these are slower. So this is not a difference of time complexity. This is just a difference of constant. So the constant factor of the arbitraries is obviously much more than heaps. So priority queues are much faster. And now what you can do is, so yeah, so you can use priority queue. Why? Because the functions that we want is the things should be able to, like, we should be able to insert things, we should be able to merge things, and merging is kind of easy. We just have to take all the elements from one of the priority queue and push it into the other priority queue. So that's what merging will be. And the other thing we want is, at a certain step, we might need to access the biggest element that is present inside the container that we have. So obviously priority queue can do that, and that too in a constant time, I think. So yeah. Um, so obviously priority queue will be better, and that's what we can do. So let's take a quick recap of what exactly do we have to do. So to do this problem, we can take this kind of thing, like we can solve it using DFS or something. So we want to take the answer for each subtree and use that to get the answer for the root, and we will do this recursively. So if we have the answer for this subtree and the actual number of moves, you can store that in a global variable. So what you can do is you can keep the priority queues here. Each one of these have a priority queue. Then you can merge all of these. So when you merge these, there's still one problem, that was that we had to add one to everything. So what should we do now? How to add one to everything? So for this we can use absolute depths. That means this is 0, this is 1, 1, 2, 2, 3, 3, 4, something like this. So instead of pushing 1 to like whatever the depth of that path is, we can just push the depth of the absolute depth of that node, and then we can subtract or add to get the actual depth, the length of the path, right? So all of these have priority queues. Now we don't have to add one anywhere. Just merge everything. Make sure you merge small to large. So small to large merging, and then everything gets in a single set. So now at the end, if this point also has a token on it, then add it to that set. If it does not have a token on it, then what you can do is you can take the priority queue and then take the biggest element in that priority queue. That will be the depth of the deepest element that is present in a continuous path. Take that element out and then add this point, right? So there will be, I think you will need to add something to your global answer at this point, right? So if the tree is like this, so let's say if this depth is 3 and this is like 4, 5, 6. So if you are removing a 6 when you are at a 3, so you can see that the number of moves that will happen are 1, 2, 3. So it is just D removed minus D current, something like this. So this value should be added to your answer. And yeah, so that's what you have to do in a nutshell. And let's see a code. So this is not really my code, but this is an accepted code that I found that is using the exact same thing that I just talked about. So yeah, I'll just show the main part of the code. So yeah, something like what they're doing is they're running so first of all, they have a lot of priority queues for each element, and then they are running a DFS. And in this DFS, what they're doing is they're taking the priority queues. So these are the priority queues. And if one of them is smaller than the other one, what they're doing is they're swapping it and then merging the smaller into the bigger one. So yeah, so that's what you have to do. Merge the smaller, always merge the smaller to the bigger. And to make sure that's happening, what you can do is you can just find the find the size of both of the, like if you're merging two things, you just have to see the size of both. And like you always want to make sure that you merge the smaller one into the bigger one. So what you can do is you can actually swap them first. If like the first one is bigger, wait a second, you have to merge the second set into the first set. So if the first set is smaller, then what you can do is you can first swap them and then merge that other set into this one. So yeah, so that's what we can do. It is almost what this person has done here, but I think a little different. So anyway, after this, it's like, I think, yeah. So after the, it is just that you just have to add the differences between the depths, right? So something like the depth of the element that you removed minus the depth of the current element. So yeah, so that's what you have to do. And yeah, so that's how you can get 100 points, because priority queue is really fast. So you can use n log square n solution here. So the final time complexity of the solution that I talked about is n log square n, which is enough for this problem. I have seen quite a few solutions that used this idea and passed pretty well. Although I think there's also a even faster solution. I think it is using segment trees. That is, I think, in total it is n login, I think. DFS, RMQ. Yes, so in the end, they managed to, yeah, so they managed to get it done using n login, using Euler tool and RMQ and things like that. So using RMQ, what they are doing is they're trying to find the deepest thing, like in the vertices, the depths we already know, in, like so something like that we will do. So when we are at node S, we don't have a token on it. We can make a query on the subtree and find the deepest token using RMQ, and then remove the token from there and put it here. So yeah, so something like Euler tool also we can do, but yeah, the solution is not very difficult. But I just told how you can fit the n log square n solution into the time limit, and obviously there are some solutions that work that way. And I think this one is better because this is more intuitive. Like we're doing it one by one, and then we are actually, so we are actually like uh, at the same time we're actually performing the movements just how they would happen. Obviously we can do the same thing in the sector solution as well, in which they're just putting a value at the index on the Euler tool, whether it is whether a token is present here or not, and then using a range query we can easily find the depth. So yeah, and also the index. So depth and index, both of the thing we can easily find using a segment tree, and then that solution is definitely n's uh, n log n instead of n log square n. But yeah, so I think this is also an overkill here. O of n log square n solution is good enough if you do not use multi-set. So they are saying multi-set plus offset, and then small to large, etc. So instead of that, if you actually use the priority queue, then I think this would be better, and that would work. So yeah, so that's that. And thank you for watching. Was my mic on the whole time? Yeah. Okay.